same thing. So I'll start first a little bit about me. I grew up in a town about an hour away called Greeley, Colorado. And as you can see from this cartoon rendition of Greeley, it's got a bit of a reputation problem. That's a whole other presentation. I like Greeley just fine. I think it's a nice place, you know, not too big, not too small. And in my free time, I like to ski and bike and watch documentaries. And this is my favorite documentary series, Modern Marvels. Documentaries like Modern Marvels and Through the Wormhole with Morgan Freeman and just those types of science documentaries and engineering documentaries, they're what got me interested in physics in the first place. So when I was trying to decide what I should do for my major, I was interested in physics, but I had zero idea what a physicist does or what it even means to get a physics degree or anything. So I kind of threw caution to the wind, just knew I liked the subject and came here. And so far it's going great. I'm a senior right now. I'll be graduating in May and defending the thesis in early April. And the reason I'm here today is because I did research with Dr. Andreas Becker in Jill. I'd also like to take a sec and talk about how I got into research for any other undergrads who are looking to get into it. So I started by just looking at posters around the wing, you know, got hung up around all the labs. And so one day I was just looking at one, and Dr. Kolanz saw me and started explaining the poster. And so later I emailed him, asked if he had any undergrad positions. And he did. His lab is an experimental AMO lab, and that stands for Atomic Molecular Optical Physics. And specifically, he made some state-of-the-art, real nice lasers. But there's the experimental side of things, so that's mostly, you know, adjusting mirrors and doing stuff like that. So I wanted to branch out a bit. One of the came up upperclassmen thought it might be cool to try to join a theoretical lab. So I emailed Dr. Andreas Becker and asked if he had any positions, and he did. But the big point here is that I emailed them, and you just got to ask mostly as an undergrad. These aren't the only people I emailed, but these are the people who I heard back from. And if you're wondering what to put in such an email, I linked another presentation up here that it has like an example email in it and just how to approach undergrad research. But I have a bigger QR code at the end, so you don't need to get it down. Okay, so what does a theory lab do? It seems like to me they just really solve hard equations. Simply. One example of a really hard equation is the three-body problem. And the three-body problem is shown here. It's trying to describe the orbits of three gravitationally interacting bodies. And this problem is an example of an equation that can't be solved analytically. And that just means you can't, like, there's no amount of sines or cosines you can put together to describe this. So you might be wondering, how did this guy in Wikipedia make this? I'd like you to discuss that with your neighbor. How can you solve an equation that cannot be solved analytically or with pencil and paper? And this is just another example of an equation that can't be solved analytically. So discuss with your neighbor.
Once you go over one day,
yeah, like these websites and this happening. You can't see like right, and you just step through it with the chain point. and add ounces. Very simple way, not very, very complicated. Like you can use stuff like that.
The overall picture is the same thing.
Yes.
You get up
Yeah,
size,
the numerical analysis, yeah. Yeah. I wonder what you
That's what I was
Yeah, that's just like an example. All right, so what do you guys come up with? Anybody wanna say?
We might be able to solve it with numerical.
Yeah, so his example was to solve the equation using numerical methods. Anybody else have anything to add? Probably not, because that's the answer. Yeah, so we can solve some of these hard problems with simulations. And specifically, in my lab, we solved the time-dependent Schrodinger equation, which describes dynamics of quantum systems, really small stuff. And we solved it numerically. And if you don't know what numerically means, you might have seen this example of the numerical method in Calc 1 or 2, Riemann sum. It's a way to integrate a function that maybe doesn't have an anti-derivative. So there's still methods of solving it. All right, so to me, what these simulations look like is, so this is me. I made a nice input file telling it what the laser should look like, what the atom should look like, and everything. And then the computer takes it and does magic to it. And then out pops a bunch of numbers that need graphing. And the numbers that I graph are usually have to do with ionization. So you might have heard of the photoelectric effect. It's an example of single photon ionization. So what this diagram shows is this is called a potential of the nucleus. And this is an electron has this much energy, so it's in the potential. It can't get out, it's stuck in the atom. But it absorbs a photon, and then it absorbs the photon's energy, and then it's up here, and it can get out of this potential. And so in the photoelectric effect, if your light is too weak or doesn't have enough energy, then this line it might only go up to about here. And then see you're still in the potential, not ionized. So not enough energy, no ionization. But then when you do have enough energy, pops the electron out and out it goes. But this is not the kind of ionization I look at. I'm looking at multi-photon ionization, which is very similar to single photon ionization, but with multiple photons. So multiple photons can be absorbed in a single step, and then you can see ionization from this breaking, where the energy of the photons is too small for just one, but if you add enough up, then you can get out of the potential. So when Einstein was looking at the photoelectric effect, he didn't see multi-photon ionization because they were just using lights or whatnot. You need, to see multi-photon ionization, you need an intense enough light. And one example of that would be a laser. So now let's talk a little bit about the laser that we use, the imaginary laser, I guess. So normal lasers, like this laser pointer, are what is called continuous wave lasers. And what that means is if you graph, the y-axis here is electric field, and then this is time. So if you graph that for the continuous wave laser, it's just one wave, one frequency the whole time. But our laser is an ultra-short laser pulse. So if you graph E field versus time, it looks a lot more like this one. And the length of this pulse, like from here to here is in the femtosecond regime, so it's a very, very short pulse. But we need such a short pulse to study electron dynamics. And electron dynamics are on the attosecond scale, so down here. So this is second, attosecond, 10 to the 18 attoseconds are in 1 second. And then we can go the other way. 1 exosecond is 10 to the 18 seconds, and that is about the age of the universe so far. So this is a crazy time scale here, but the small time scale. Okay, and when we're talking about our laser, one of the parameters we can talk about is the pulse length. So each one of these little guys is just supposed to represent an electric field cycle. So if we look on this page, it's like one whole cycle. So our cycles can be, so our pulses can have different number of cycles in them, but still think of it as a single pulse that looks like that. It's not like multiple pulses. Right? That's an important distinction. And okay, another parameter we can talk about is the laser's intensity. So here we have like 2 3-cycle pulses, but this one is much more intense. And that just means that there's a lot more photons per cycle. And if you don't know, a photon is a particle that represents one quantum of light. So it's like where the energy in light is. Okay, now I want you to discuss with your neighbor again. What happens to ionization if the pulse length increases? And also, similarly, what happens to ionization when intensity increases? Discuss.
Yeah. If you hit hitting it hard, yeah. There's a probability that's going to start to expose.
If the intensity improves, what you get right now, we're right, but if the amount of particles delivered is the time is the same, why would
Yep. No, we're saying as the pulse length increases, that means that it's going to be less.
same number of photons, but
Spread over a longer.
at the snack, I agree.
Yeah. Just changing the color.
Okay.
Yeah.
And yes, that would decrease it.
Whereas intensity would increase intensity, more change in the kid.
Yeah, either way, I'm thinking of it.
Yes.
It's big photons per curious.
Yeah, you get more chances to
I interpreted the first one, you're just keeping the density the same, just federal.
Yeah. Yes. Yeah. Yeah.
I just thought that this was really class and gives me a lot of praise. Yeah.
All right, so what'd you guys come up with?
I suggested that if the length of the pulse increases, there's a greater chance that electrons get in your target area while the pulse is there, therefore probability goes up. intensity, I've got a problem with this, but if greater intensity, then are you hitting more photons, and so the picture you showed earlier coming out of the well, more photons means greater chance of you leaking out of the well therefore ionized?
Exactly, yeah. Yeah, so that's exactly what I'm trying to get at. If you increase either one of these parameters, we think that ionization should also increase. All right, so we're going to be looking at a lot of plots like this for the rest of the talk. So take a sec to explain it. On the x-axis, we have intensity of the laser, and then ionization on the y-axis, and then the different lines represent different lengths of pulses. So this blue guy is a 1 cycle pulse, and this guy's a 10 cycle pulse. And then you can see, mostly from this graph, if you go to a longer cycle, or a longer length pulse, then you see more ionization, or if you go higher in intensity, more ionization. But this isn't the way we look at these graphs. The way we look at it is on a log scale. So what that means is the y-axis is now in orders of magnitude instead of just incremental steps. So in between each graph notch is a different length, as opposed to this one where it's the same. But the reason we do this is because, so this is the same functions being graphed, but it is a lot easier to see this one. People love linear things. And this also has the added benefit that you can see the ionization of the 1 cycle pulse here. See, it goes only up to about 10 to the negative 4, so that's 0.0001. So you can't even see that in this graph. It's like all the way down at the bottom. So this is the type of graph that we'll be looking at for the rest of the time. Okay, so this relationship here, this graph is what we hope ionization looks like on the graph. However, these people around 2007 are saying that that's not what they're seeing. They're seeing, they call it anomalous ionization, which is where I got the word from, if you were wondering. So yeah, so this is what they saw. This is some of their graphs, or one of their graphs. And it's the same graph that we were just same axes and lines of the graph we were just looking at. But we see here with the 1 cycle pulse and the 1.5 cycle pulse down here have more ionization than the longer pulses. And remember we said if we have longer pulse, we should have more ionization. So this paper didn't describe, didn't give a reason to what was causing this anomaly. But the people in my lab thought they knew, and that was my job, was to try and figure out what was going on here. And the first place they pointed me to were these equations. These equations are how we represent the laser in the computer. And this is the A field of the laser, and then this guy's the electric field of the laser. And it's not super important what the A field is if you don't know, but it can be thought of so voltage is to electric field as A field is to magnetic field, kind of like that. But the important thing here is that we define our laser's A field first, and then we take the derivative of it to get the E field. And when we do that, keep taking derivative of a product before, you get 2 terms, right? But this second term sort of messes with our laser a little bit in ways that we don't initially think would happen just by setting the A field. Yeah, so here's the exact same thing as the last slide, but a lot easier to see with graphs. So this is 1 cycle pulse. And then if we just graph the first term, the A field, you get this guy. It might be a little hard to see, but it's like a sinusoidal function that's nice and inside this envelope here. So that represents how we think the the laser looks when we put in that equation. But this blue line is what it actually looks like. We'll talk about it in a sec. It looks different because of that extra term, right? But we'll talk about what that means for ionization in a sec. First, if you look up here, the 10 cycle pulse, I'm graphing the same stuff here. So there's what we think it is and what it actually is here. But if you notice for n equals 10, you can't even see the other line. So what this is saying is that this effect is mostly seen on short pulses. And if you remember, the anomaly we were talking about was also a shorter pulse effect, which suggests that this could very well be what's going on. Okay. So there's another way we can look at the laser. This graph is the same as the n equals 1 graph, except for this slide, we're graphing electric field over time, and for this graph, we're doing like in amplitude versus angular frequency. If you haven't seen the relationship before, energy is related to angular frequency by a constant. So this graph can sort of be thought of as a graph of the energy of our laser pulse. And so again, this is the one that we think we have, and then this one is the one we actually have. So you see that our laser has more energy than we think, and so theoretically we should see more ionization than we think. But to test out that hypothesis, we need to find a way to solve this frequency correction problem. And people in my lab have done that. They published a paper on it. So if you know that you set a frequency that you want your laser to be, and then you take the derivative and the frequency gets moved up, then you simply set your frequency as lower than you want it to be, so that when you take the derivative, the central frequency gets moved up to what you think that it should be. So that's the idea behind how we fix the frequency shift. Okay, and remember, this is their data. They're seeing more ionization for short pulses. And then the next slide, this is my data. It's a little scaled differently, but this is exactly the same points and intensities and lengths that was in the last graph. And as we see in this low intensity regime, there is, in fact, a bit of an anomaly. It's not quite as pronounced as theirs was, but it's definitely there. There's also some other weird sort of effects going on. But once we correct for the frequency correction, all of those effects really wash away when we see what we expect we should see. But if we want to know more about this anomaly, we have to look at other atoms as well. So far, we were just shooting hydrogen atoms. But for the rest of the talk, we'll be shooting beryllium atoms with our laser. So there's a few more electrons and protons and whatnot. So when we do that, this is my data for a beryllium atom. And for the non-frequency corrected version, again, we see some more pronounced anomalous behavior, which is then mostly washed away in the frequency corrected version. There's still some going on there, but we can see that this effect is probably like 90% to do with the frequency correction. Yeah, but also now we notice this other strange area, which is another anomaly now that we can try to describe. And if you notice, it shows up in both the corrected and the non-corrected version, and it's also in the opposite regime of the first anomaly. So now we're in the high intensity, longer pulse regime. And if we want to try and understand the second anomaly, we gotta look at what's happening to the atom when the laser's hitting it. Okay, start out with a weak laser. So I know I said you need an intense laser to get multiphoton ionization, but I think a laser that's weak enough that it can still have multiphoton ionization. So this is a 5-photon process. This is exactly what we saw in the last ionization graphs, where this is the ground state, and then up here is the continuum. And so if your electron gets the energy to push it up above here, then it's free. Okay, so that's with the weak laser. But if we have an intense enough laser, then the continuum shifts up with the intensity of the laser. So if this is like time down here, and then this is the what the change in the continuum energy as the laser goes by. So as we can see, with 5 photons over here, we do not ionize, and we're still bound to the atom. And so that's more for longer pulses and for shorter pulses. And to understand why that has happened, we can look again at the graph of the angular frequency versus in amplitude. So if you remember in the graph before, this is the graph where we're basically graphing energy on this axis. And then this is the longer pulse, and this is the shorter pulse. Notice that if you graph it like this, the longer pulse is narrower. And what that indicates is that the photons in our laser, so if you take a random photon, then this represents the probability of what energy it will have. So the higher up on the y-axis, the more probability, and then on the x-axis, that's how much energy it will have. So if we look at the full width half mass of the long pulse, most of the photons will be in this energy region here, and then there's a lot bigger of a region here for the short pulse. So the idea is that if more of the photons are similar in energy, and you have a channel closing, then that's going to matter a lot more than if you have a spread of energies, and you could possibly just absorb a photon with a different energy, and then maybe the channel looks like it's not closed. But yeah, so that's why it will matter a lot more for the longer pulses the second time. And now I'll just give you a quick rundown on a day in the life in the lab. For me, I usually get up and go to class first, and then get to lab and decide if I need any coffee, get some coffee, check my simulations to see if they're done. If they are done, then I can graph all the stuff in different ways and try to see what I can make of it. If they're not, then I research what other people are doing in the field, try to understand what's going on better. And yeah, thank you. Do you have any questions?
One of the graphs, it looked like the end that was 0.5 actually showed us the highest in the non-directed, and then also in the directed was second. Yeah. So how can it be that the 0.5 is the one that actually is most high?
So when we're down here, we're seeing what's called short pulse effects, and so it's hard to know exactly why this. It'd take a while to look into this and see why, but it's probably because of some short pulse effect that we weren't taking into consideration. And then if you wanted that QR code, there it is.
I have a quick question. What do you enjoy most about your research? So what part of that flowchart is the best for you?
The top.
well, besides the copy, of course, I really like making graphs. I like visualizing data and whatnot.
Just curious, how long do these simulations take?
Yeah, well, that depends on a lot. It's like, you give it all the parameters, but they have to be like discretized or whatever. So you set like a box that this is taking place in, and depending on that box and other parameters, it could be like anywhere from I've had some that go like a week and a half, and everybody's mad at me, and then I have some that are like